Good morning to everybody. Myself, Surendra Singh Kachhwaha, Professor in Mechanical Engineering, Pandit Deen Dayal Patel University, Gandhinagar. Today, I am going to deliver a lecture on wind energy technologies. It is a very relevant field, and across the world, a lot of activities are going on in this area. This is my team at Gandhinagar, Mr. Nagababu Garpati, who is doing PhD in wind energy, Vimal Sasani, he is working in the optimization areas, and one of my MTech students, Natas Naidu, he is working in offshore wind energy. Today's talk consists of the two parts. Part A, related with the wind energy, and Part B, if the time permits, then I will talk about the offshore wind energy and certain case studies. In Part 1, I will cover that what is the motivation behind wind energy, then the scenario related with international and Indian scenario related with wind energy, couple of wind energy fundamentals, then how to collect the wind data. Besides this, a couple of case studies which I have done that I will include, and other thing is that what are the existing technology related with wind turbine configurations, that is horizontal axis wind turbines and vertical axis wind turbines, and further the recently what are the issues and challenges related with the development of wind energy. Now we know that almost if you just look at the data in this particular graph, you will see that in 1971 the total consumption of energy, which includes industry, transportation and others includes agriculture, households and various other sectors. This total sector says that around 440 million tons of oil, equivalent oil, were the total consumption in 1971. In 2012, this consumption has grown up to 4 times, that is 1,626, 440 to 1,626. It means 4 times energy consumption has increased, and due to this increase in energy consumption, there is a severe impact on the environment. Let us see that what happens in the environment. In 1971, the total, due to this consumption of conventional resources, the total consumption of CO2 was 15,600 million tons of CO2 that was emitted in the atmosphere in 73, and in 2012 the total consumption of electricity CO2 emission was around 31,000. It means double CO2 has been emitted. So almost there are a lot of stress, a consumption of our resources, and due to that one there is a severe impact on the environment. So that is the biggest drawback of using the conventional energy resources. Now, two things I have told you. Depleting conventional energy sources are a big issue, and due to utilization of conventional energy sources, we have environmental concerns, which includes global warming, greenhouse effect, increase in carbon emissions, climate change. All these issues are there, and nowadays in newspapers, scientific magazines, everyone discusses about those things. Now, since I have to talk about wind energy, let us see that how wind energy stands in comparison to the other type of resources. Say, suppose if you consume coal, then the total tons of CO2 emissions per gigawatt hour generation of electricity. 1 gigawatt hour is nothing but 10 to the power 9 watt hours. A gigawatt hour is a unit because it's almost a very big unit. It is there. So 1 gigawatt hour electricity generation means it consumes coal. Due to coal, the CO2 emissions are 964, and oil a little bit less. It is 7,026, and in the case of gas, it is 4,084. Now, as these are the conventional energy sources, as compared to that, if you compare nuclear, it is hardly 8. But there are other issues are there with nuclear energy. Then with wind, it is only 7. This 7 is, as far as the operation is concerned, there is no CO2 emission. But when you manufacture the blades, steel structures, and various other things, in that case, conventional electricity is consumed, and due to that reason, the figure of 7 comes. If you compare the solar photovoltaic, it is around 5, and large hydro, it is already 4. So, point is that wind energy, among other sources, a very minimal CO2 emission is there. So that's the big motivation to expand the wind energy. Normally, people ask a question when we apply the wind energy, what is its competitiveness as compared to the conventional resources, because ultimately all decisions are taken based upon the economics only. If you look at the 2008 and comparison with 2018, the left hand side of this graph, that is, you can say, least competitive, means they are quite expensive. Commercially viability is not there. Whereas right hand side means the most competitive. So conventional resources in the last decade were, say, gas, coal, nuclear, etc. They were quite competitive and price was quite less. Electricity per unit was quite less. Whereas in the case of tidal, solar, offshore, onshore wind energy, biomass, the price was quite high. Due to that one, they were less competitive. But just in this end of this decade, means 2018, near after 2 years, 3 years, or end of this decade, you will see that the gap between the conventional resources and renewable resources, this conventional resources and renewable resources is reducing. And we will see that either end of this decade or maybe at the somewhere around beginning or in the mid of the next decade, almost you can say this renewable resources will be competitive, commercially viable as compared to the conventional resources. Solar already, as a mass scale, it has already spread. This wind energy already spread. So due to that reason, now they are quite comparable as compared to the conventional resources. One of the biggest event which occurred, can say, during the COP21 convention was there in the Paris, and India has committed a huge commitment as far as the renewable resources are concerned. The total they have to total cumulative capacity up to 2030. 40% of the cumulative capacity must be by means of renewable resources. It is a huge quantity, and therefore, to achieve this target, a lot of work from government side as well as from the industry has to be done. So, due to this commitment, wind energy can play a very important role, and this target, to achieve this target, wind energy will play an important role. Even if you just consider the data of 2015 and 16, grid interactive power capacity of 4,460 megawatt via renewable energy source, this was the target of the government. Out of that one, 2,400, around 53% belongs to the wind energy. The wind energy will, at present, among the renewable energy sources, playing a very important role, as well as in the near future, the wind energy source will play again a very important role for the development of the country. So this is the recent, almost since the India has committed for this one. So due to that reason, we have to expand, we have to think, and we have to implement the renewable energy. Now, two things we have discussed: the depleting conventional resources and the environmental concerns. Environmental concerns means how to reduce the carbon emissions. That is a big issue. Besides this one, remember that as far as the energy security is concerned, this is a very important figure. 1.39, that is 1.4 into 10 to the power 6 gigawatt hour. This is the estimated demand at present. 2016-17 means this is the estimated demand in our country, which includes industry, other sectors, all other things are there. Now, this requirement will rise up to 2021-22, that is roughly around 50% increase. It will be 1.9 into 10 to the power 6 gigawatt hour. Almost can say 50% increase requirement is there. How to fulfill that one? We cannot stress, we cannot rely totally on this conventional resources, that is coal and other things. We have to switch over to renewable energy sources. And how renewable energy sources can fulfill this demand, a particular case study I will also discuss. Now, this is just data, wind energy, almost you can see the red color, it is there. 2400 around in the financial year 2015-16, 2400 is the total installation of wind power, which is higher as compared to the solar. Solar is 31%, and installed capacity around say it is 421, and the total cumulative installed capacity is around say 24,000. Up to total this installed capacity, 24,000 megawatt is related with wind energy itself. Waste to power, still it is a developing stage, but a lot of scope is there in the industry. We will talk some other day. Now, that was the scenario as far as our country is concerned, where wind energy development was there. Now, let us see that what's going on in the case of developing world and developed world, particularly as compared to Asia, where we stand. You will see that People's Republic of China, the highest share is 31%. This is the data of 2014, and still the list remains the same. China almost can say even total share of wind energy is 31% for China. USA the second one, and in European countries the two big names are there, Germany and Spain. India among these countries, we are at the fifth rank, where it is data is slightly over 22,000, around say 24,000 it is there, and the total contribution of wind energy across the world, we are contributing around 6.1%. Other big names are United Kingdoms, Canada, France, Italy, and rest of the world around say 15.8% they are contributing in wind energy. So the point is that a lot of activities are going on wind energy, and you can see that in this graphics, People's Republic of China, they have a large fraction in which a lot of stress is given on wind energy. So this is the data related to the energy. Now I'll talk about wind energy fundamentals, some historical perspectives, and which includes wind energy measurements, because investment is required, and once the investment is there, so it should be based upon the past data and what are the instrumentation used in this case. Historical perspective point of view, Heroes windmill, that was the first century AD/BC, AD/BC, it was used, and in that case, it was almost can say for grinding of the grains it was used. Then in the 17th century in the Iran, cistern windmills were there for cooling of the buildings. It was used. Then in the last century, post windmills in the Europe they were using. Smoke mills in the Europe they are also using this design. And besides in United States, they are using pumping of the water by using the windmills. Up to 50s and 60s, the windmill started. But as the development of internal combustion engine come to the picture, then all these windmills disappeared. Because in that case, the petrol price was quite cheap, and or diesel and petrol was quite cheap. Due to that reason, what happens? This windmill application was minimal, and people started using internal combustion engines and generator sets. And due to that reason, the progress in wind energy was halted. But again, due to environmental concerns and the price, of course, price at present is quite low. But one of the reasons is that climate change and other issues are there. Due to that reason, people are switching over to the conventional energy sources. These are a couple of designs. In 1961, Chekhov turbine was there. These are all in terms of kilowatts or less than kilowatt designs. Dennis also, they are wherever the wind velocity is quite reasonably good. These designs were there, and Europe a lot of progress has been developed. So Dennis Getzer wind turbine was there. Then Smith Putnam wind turbines. So these are almost these are the developments in 1980s and 90s. It was there. Now the most important part is the wind energy. Wherever the development of wind energy is concerned, the data collection play a very important role. Suppose I want to install a particular windmill at a particular location, then I should know that what is the nature of the wind, what is the magnitude of the wind, what is the direction of the wind, and how much quantity it is coming at a particular point. So for that particular purpose, normally wind data collections are used, and in that case, anemometer is a very important device, and almost you can see that at different heights, normally you can say 10-meter height, 40-meter height, and sometimes more than that particular height, this anemometer is provided, and this anemometer continuously for around the year, it measures the velocity, direction, and besides this one, other parameters, for example, temperature and atmospheric pressure can also be measured. And all these data are accumulated in data acquisition system, where round the year these data are there. ISRO, Indian Space Organization, they are also manufacturing this particular data acquisition system, and in a very minimal rate they are selling it, and almost even as academic institutions we can put it and we can collect the data round the year. Maximum cup anemometer is also used in USA, where based upon the friction that continuously you can say sine wave is generated, and the nature of the sine wave, the velocity is proportional to the wind, and based upon that one the wind velocity is stored. Propeller type anemometer, normally you can say any wind is having fundamentally three directions. Other two directions may be very small, but to measure the complete three directions, we have the three air components are there, and through these three air components, we can measure the three components, and finally we can find out the magnitude of the air. So almost anemometers, wind vanes, thermometers, barometers, all these quantities, these are the devices through which we can measure the data, and we can collect the data around the year, how the variations are there, we can easily find out. Now, since the investment is quite huge, so recently developed techniques are LiDAR, that is light detection and ranging. That is, the point is that normally you can say this windmill, horizontal axis windmill, it is around say 80 meter to 120 meter height, it is fixed. So due to that reason, at that particular point, how much is the wind velocity available? So to find out that one, the device used is light detection and ranging, LiDAR. It is quite expensive, but it can easily detect, because it is based upon the remote sensing principle, where light will be thrown, and then based upon resonance and scattering process, they can easily find out that at a particular point what is the velocity it is there. Besides this one, another device is sonar device is there, where sound detection and ranging means the sound waves are sent, and then based upon the sound wave, how much reflection it is coming, again it is based upon the sound scattering process, one can easily find out how much is the wind velocity at a particular point where we install the wind turbines. So these are the two important devices, but they are very expensive, but they can give a quite accurate answer that what would be the available, because ultimately when investments are there, for decision makers, for planners, they have to take a decision. For decision making, data collection is important, and these devices quickly measure the wind data, and based upon the wind data, the manufacturer or the developer of wind farms can take a decision whether they have to install the wind turbine or not. The most important part, as I have discussed, is the wind data sources. Now, in our country, the agency which deals with the wind data collection is the CVET. It is the head office is in Madras, and its various in situ wind data collection, on-site data is there, which are physically measured using the wind mast. So at various locations, particularly in the coastal areas and in various states, they have their own measuring devices, and the continuous measurements are there. And as an open literature, you can go to the website of CVET and you can collect that at a particular location how much is the measured data collection is there. So almost on average basis, per day basis, they can provide the data, and based upon that data, the calculation can be done, and based upon the calculations, one can design a wind turbine, a small capacity or maybe a big capacity, depending upon the data analysis. In situ wind data is just because measured data, and they are very highly reliable, and based upon that, one can take a decision. Besides this one, now the point is that at every point you cannot measure the data, because it is highly expensive, and plus a lot of investment is required. So due to that reason, what happened? Satellite data play a very important role. In that case, satellites like QuickSat, WindSat, OceanSat, Aquarius, and various other agencies are there, ISRO and NASA. They measure for the complete Earth, or in our country, almost can say each and every grid, each and every place in our country, the data is there. If you go to ISRO website, you can find out. If you go to NASA website, there also the open source literature is there, where you can find out the data. And each and every grid, you have the per day basis, average basis, you can find out the wind velocity, and based upon this wind velocity, you can calculate the you can analyze the data to find out how much power available through wind energy. Besides this one, other type of data are reanalysis data sets, which are normally generated by interpolating the data collected by the satellite. Because satellite data, what happens at very low velocities, they have some uncertainty, higher uncertainties, maybe around more than 10%. So due to that reason, some interpolation is required by using reanalysis data sets. In that case, again, a lot of open sources are available, NASA, MERA, and ECMWF, that is European Center for Medium Range Weather Forecasting. All these centers are there. Using those centers, data availability is there, and those data can be utilized for analysis purpose or assessment purpose. So open source point of view, a huge number of data is available. Sometimes commercial level, various WASP and softwares are also available. they are also selling the data, because this data has become a big business across the world. Now, after this wind data collection, let us talk about that. Once we have the data, then how to proceed further, because this data collection part through satellite or through in situ data, that is through measured data, you can use them, and based upon that one, how we can analyze that one. Now remember that as we know that from the Earth's surface, as you move the height wise, the upward direction, the wind velocity is higher due to boundary layer formation. Most of the cases at 20-meter height is normally standard height, 10 or 20 meter height, where the data are measured and data acquisition takes place. Now the point is that wind turbine, normally it is installed around, say, earlier it was in the 90s and 2000, it was installed around, say, 50-meter height, but recently almost it is either 80-meter or more than that one. In some of the cases, the total height of this wind turbine installation is around, say, 120-meter also. So now the point is that data has been measured at 10-meter or 20-meter height, but we have to convert this velocity up to 80-meter or, say, more than 80-meter, 100-meter or 120. In that case, a well-established log-log law is used, and using this law, we can convert the velocity at 10-meter or 20-meter into the requisite height of 80 meters. I'll just show you that one. And once we convert that velocity at 80-meter, where we want to generate the power, at that particular point, using the data, we can convert into annual mean wind speed, annual power density, and capacity factors. These are the important parameters to generate the power. And based upon that particular, how much we can get this value, based upon we can take a decision for installation of wind powers. And finally, ultimately for a designer or administrators, the important point is that he will not understand all these things. He will simply ask a question: how much is the power generated through this site? Ultimately, you can say power generation site calculation is a very important one, and this is not a rocket science. Everybody can do that. So this is left-hand side diagram represents wind velocity. Normally, you can say through boundary layer we show a curved profile, that is the average velocity it represents, whereas the actual measurement is somewhat zigzag. So its average value comes as a smooth line, and as we move in the z direction, the wind velocity v increases based upon the profile shown in the diagram. The point is that as you move, the wind turbine is installed higher at a more height. In that case, the more power can be generated. But at the same time, the cost of the structure, that is the pillar cost, will be quite. So 20 meter. Now in this case, we have measured the data at 20 meter using this formula, where r is the reference point and Vz is the point at which we want to generate the electricity. Using this formula, relative formula, we can find out that at that particular point we can calculate this wind velocity, and that is the key parameter. Based upon that one, ultimately we have to generate the power. This is almost since this is the data available near the coastal area of the Gujarat. Certain 5 or 6 locations are there: Verawal, Oka, Dandi, and Devgarh. So based upon that in situ, the measured data, we have converted into monthly average wind speeds at 80-meter hub height. We have converted those data using the log-log law into average wind speeds, and then wind speeds for different months it is there. Now look at the peak between May and August. It is in the monsoon season and pre-monsoon season also there. Remember that in northern India, this is the summer season in which almost huge amount of electricity demand is there. So this kind of in the southern side we can have this electricity, and we can take advantage of wind energy, and this can be connected to the grid, and more electricity can be generated by using this wind energy. So this is the graph we have drawn. You can also convert into equation form, that is known as the wheel-bull distribution, where in the form of equation you can convert. Normally this wheel-bull information is available in any wind energy textbook. It is available. Now once the wind velocity is there, this velocity is converted into wind power, and we know that power is proportional to the cube of wind velocity. Slight increase in velocity, almost you can say a 29% increase in velocity will create double the power. So almost you can say that is the main salient feature, because power is proportional to the cube of wind velocity. So in that case, again, you will see that particularly in coastal areas, between the month of May and September, peaks are there in almost all the major data, and this peak is very suitable for wind energy, electricity generation using the wind energy during that particular season. The wind power density gives an idea that how much potential it is there for generation of power. Higher is the wind velocity, better is the power generation. So these are the summary of the data. Most of the cases, in the case of the case studies which I have done near the Gujarat, velocity, average wind velocity is more than 5 meters per second. This is considered to be reasonably good wind velocity, and equivalent mean power density around most of the cases around 200 or 150. They are the good scenario or very good scenario as far as the power generation is concerned. And this is the power generation calculation based upon 80-meter height. If you go more than 80-meter height, then this quantity will further increase. So based upon this one, if you use satellite data, in that case you will see that at the upper graphs represents the wind mean speed, left hand side is the mean speed of wind, and right hand side is the power density. So you will see that on the land, 50-meter height, almost green color is there, and if you go the bottom graph, it is 80-meter height. In the case of 80-meter height, the yellowish color is more. It means as you go the height, more height, the point is that wind velocity will be quite high. And equal right hand side graph represents the wind power density. So more is the red color, red color is on the sea side, and over that one the blue colors are there. Means the point is that wind this power density will be much higher. So particularly in coastal regions, a lot of scope is there. But not only the coastal regions, one have to calculate on the northern part of the country also, northern India also, so that what is the potential available based upon that technology can be developed. These are the CVET has given this map where almost can say the red colors are a good wind velocity ranges. Then green is also better than that one, and finally almost can say a couple of areas where almost can say this light blue color is there, where almost can say wind velocity is quite high, and it is there. But it doesn't mean that in northern India there is no scope, because all these things, technology etc., they are textbook technology. They say that okay, for technology development is only for this particular high wind velocity. Nowadays, lot of changes are there, where generator has been advanced, wind turbine has been advanced. So one have to renew its interest to examine that what is the scope in the case of northern India, particularly in the case of northern of Rajasthan, where Punjab, Haryana, Uttar Pradesh, almost you can say at 12-meter height one can develop the wind energy also. Normally you can say a capacity utilization factor is important, means it is that whatever, suppose if you install 1 megawatt, then 1 megawatt out of that one, round the year wind is not available. How much time it is available? If it is 20% time it is available where the wind is electricity generated, then we can call it as 20% CUF. So in the case of wind energy, if the value is more than 20%, then it is economically viable. So most of the cases when the power density is more than 200, up to 200 or more than 200, and even more than 400, the CUF, that is capacity utilization factor, is around say 20 to 32. So in that case, economically it is viable. This is the data for onshore, means on the land itself we can generate the electricity. Normally capacity factor can be defined as AEP, that is annual energy production, that is how much kilowatt hour in per year you can produce, divided by rated power. Rated power means how much this installation rated capacity is there, say for example 1 megawatt or 2 megawatt, depending upon how much system you are using, and the 8760 is the number of hours in the year. So this ratio is a very important one. This is called as capacity factor or capacity utilization factor. Using this factor, almost you can find out how much fraction you can generate. Now, once you have this idea of this capacity utilization factor, then each device or any windmill or wind turbine performance curve is there, or turbine characteristics curve is there. Here, I have considered the two turbines. One is the 5 megawatt RE turbine, RE power turbine, a manufacturer's name, and G manufacturer is that 3.6 megawatt turbine is there. So this particular curve, each curve has its own nature. Say for example, for the case of G 3.6, where almost you can say we have a smaller curve inside the lower curve, we can have the different characteristics. Rated capacity is 3.6 megawatt. Cut-in speed. Cut-in speed means above this speed, only the wind this electricity can be generated. Below this, the turbine will not work. Cut-out speed means it is the maximum speed at which afterwards turbine will not rotate. So that is 27, which is quite high. Particularly, you can say only in the case of stormy season, the velocity increases more than that. Otherwise, always can say wind velocity will be lower than that. Then the rated speed is the 14 meter, where when the 14 meter speed is achieved, in that case, the turbine will work at its own rated capacity. With maximum power, that is the rated capacity is 3.6. So at 14 meter per second, it can generate the 3.5 megawatt. Megawatt multiplied by hours. Then normally you can say a blade is optimized for can say 3 blades. So that's why it's a 3 blades. Most of the cases now 3 blades are used. A rotor diameter is around say 111 meters. At 80 meter height, the can say radius will be around say 55 and diameter will be 111 meters, almost equivalent of a football ground. Then the swept area based upon the diameter, it is 9,677 meters square. Almost you can say this kind of sizes are available, and even people are going for a bigger than this one also. Now, data measurement is important. Data and satellite data is also important, which are through open source you can find out. Now, once the data sources and other things are available, and you have to select the turbine characteristics, and we have seen that this performance curve is available. So now the point is that what are the different technologies are available as far as the choices are concerned. Because ultimately you have to store the wind power. In that case, there are two categories, two main classifications are available. One is this horizontal axis wind turbine, which is almost which can be classified almost axis is horizontal, and its classification is Dutch windmills, then multi-blade water mills, high-speed propeller-type windmills. So most of the big-size wind power turbines are concerned. Almost you can say horizontal axis is the preferred one, because manufacturers have developed like this, and most of the key players across the world, Gamesa, this RE Power, and Siemens, various other big manufacturers across the world, they are manufacturing in terms of megawatts. Even a single turbine, earlier it was 1 megawatt, now it is 2 megawatt, and even people have gone up to 3 to 4 megawatt also, a single turbine, because the commercial viability is there. Other category is the vertical axis wind turbines, where almost you can say axis is vertical, and across the axis the revolution takes place. These turbines are classified as the Arrhenius turbine, and due to lift forces, the movement takes place because aerofoils are there, and aerofoils, the lift force causes the aerofoil shape of wings to rotate. And besides this one, another design is Savonius design. Based upon the drag forces, the rotation takes place. Other less known devices are Sweeney type, cistern type windmills. These are the two other things are there. But most of the commonly used are the Arrhenius and Savonius as far as the vertical axis wind turbines are concerned. So, left hand side of the slide represents the top figure represents the horizontal axis wind turbine, and the bottom represents this particular, you can see, left force side Arrhenius type of design. Now let me first discuss about the horizontal axis wind turbines, and this classification is based upon the diameter of the rotor. So y-axis, if you look at it, is based upon the meters it is available, and initially you can say, normally you can say household type of wind turbines, they are less than 10 kilowatts and their height is less than 50 meter, 25 meter height or 12 meter height or 15 meter heights they are used. Then the point is that at present these are commercially not viable. Not commercially viable means in our country no manufacturer, there is no manufacturer which can produce less than, in terms of kilowatts, nobody is producing. Even in foreign countries also a limited manufacturers are available, but there the price is quite high for the case of electricity. So due to that reason, almost you can say they are manufactured in a small quantity. Then slowly and slowly the capacity is increasing, 100 kilowatts, then 200 to 250 kilowatts. Besides this one, now if the capacity is around say 500 kilowatt, we can call it as medium-sized wind turbines. And big-sized wind turbines, almost large wind turbines, if it is in terms of order of magnitude is megawatts, then you can call it as a large wind turbines. At present, around say, particularly Rajasthan, Jaisalmer, 2 megawatts they are using. In Gujarat also, the Inox, Siemens, they are producing 2 megawatt capacity wind turbines. So as far as the big size wind turbines are concerned, horizontal axis wind turbines are well developed, and industry this design is well saturated and almost commercial level. They are most of the part of the world they are used or installation of to generate the electricity. Some data are there. Classification point of view, small scale we can call it as a micro, mini, and household, and the diameter varies from 0.5 to 1.25, and household the diameter varies from 3 to 10. Then small commercial type of things are diameters are 10 to 20, medium commercial 20 to 50, and large commercial almost you can say 1 to 3 megawatt. We can call it a large commercial type of wind turbines. For small scales, main manufacturers are small A, Wind Power, Aeolus, UG, USA. These are all small scale manufacturers, not much big name. But in the case of large commercial type of manufacturers, big names are T-Power, Gamesa from Spain, Vestas, Mitsubishi, Suzlon, Inox Wind, etc. These are the almost big names across the world. When we talk about horizontal axis wind turbine, wind direction can say when the wind direction moves towards the wings, then we can call it an upwind type of wind turbines. And if the wind direction is from the downstream side to the upstream side, then we can call it as the downwind. Downwind turbines almost you can say there is no need of adjustment; they can adjust itself. Whereas in the case of upwind turbine, the mechanism is required. Nowadays, most of the designs are based upon upwind design, and the yaw mechanism is there, in which the front will always be in front of the wind coming from wind crossing this particular wings. Main components in horizontal axis wind turbines are rotor, hub, then this Nestle cover, which includes the control systems. Driving trains are required. The reason is that the movement of the wings are quite slow, and for generator purpose speed is required. In that case, a gear mechanism is used to increase the speed. And rest of the things are main frame or yaw system, in which the direction of the movement of horizontal axis is given, and others are you can say electrical components are there. In this case, the point is that height is 80 meters, so therefore the reliability of the product should be good, because ultimately maintenance almost the life is 20 years, and up to it is expected that up to 20 years no maintenance should be required. That's why the very high quality reliability of the product is required. And besides this one, the tower cost is quite high, and these horizontal axis wind turbines are quite, I can say, efficient as compared to vertical axis turbines. These design, as far as the wind energy is concerned, this design of horizontal axis is concerned, the technology is well developed, and in terms of megawatts, it is easily available in the market. So that's why can say the feature of horizontal axis wind turbine is that it is stable, ability to wing wrap, and pitches across the blade can also be varied, and they can, in a very high strong wind velocity, they can also work, and they are self-starting. Certain drawbacks are also there. The drawbacks includes transportation cost is high, because ultimately you can say the single wing radius is around 50 meters. So transportation for special purpose transportation trucks are required, and a tower construction is also very strong. It is required because the height is around say 80 meters, more than 80 meters. So strong tower construction. And another is NIMBY issue. NIMBY means not in my backyard. People want electricity, but the point is that some ringing sound is there. So due to that reason, nobody wants the wind power, this particular turbine, nearer to their houses, because it affects due to its irritating sound. It affects on their health also. So people want it, but people want away from their houses. Besides this one, maintenance. If the product is very high quality, it's good. But whenever the maintenance is required, the cost of maintenance is quite high. And besides this one, additional yaw control mechanism is required. Due to that one, we have to give a guidance that whenever the wind, in which direction the wind is flowing, in that we have to keep the rotor into that particular direction. Therefore, that mechanism is known as yaw control mechanism, and that can be that is always an integral part of this particular system. Now, this till now I have discussed about horizontal axis wind turbines. Now, as far as the vertical axis wind turbines are concerned, we have the most popular design is the Darenius turbines, which is based upon the lift forces. And in that case, the axis around the vertical axis, the wings are provided in an aerofoil shape, and based upon that shape, the rotation takes place. These systems are less efficient as compared to the horizontal axis, but still they are quite popular because in the case the symmetry is there, and at the same time, in this system, the main advantage is that they don't bother about the direction of the wind. Whatever the direction of the wind it is there, they will rotate. As compared to horizontal axis, in that case, direction is not an issue. So there are certain advantages are there as well as disadvantages also exist. So this is a Darenius type turbines, but normally you can say they are always a small capacity. Maybe you can say less than 10 kilowatt, or in terms of kilowatts they are utilizing. Till now, in 90s, people are using in terms of megawatt this can say this Darenius type of rotors, and normally you can say if the blades are not curved, then we can call it as H rotors. Now again, a renewal interest is there, and I have heard a lecture from a professor from California University. They say that research has been a lot of research is required for development of this type of turbines, and they are trying to develop a 20 megawatt capacity, a big size of this particular rotor. So this is at a developing stage, and once it is developed, then it can compete with the horizontal axis wind turbines. So in that case, not only the wind aeronautical engineers are involved. Besides this one, you can say structural engineers, structural rigidity, maintenance, other aspects are also important. After Darenius, the other important vertical axis turbine is Savonius turbines, in which a scoop is used where the two scoops are there. So across this side, this friction is less, and therefore it rotates in the clockwise direction. And sometimes the scoop is also given at the bottom. Different shapes are there. For self-starting purpose, 3 scoops are provided in the center diagram. So whenever the wind velocity is there, this is based upon the drag. Whenever the drag-based design is there, it is less efficient. But at the same time, at a very low height you can install it, and the generator is at the bottom side. And in that case, since the generator is at approachable height, so due to that reason, the maintenance cost is quite low, and at the same time, whatever the direction of the wind it is there, it is quite suitable. Again, the point is that this is less efficient as compared to horizontal axis wind turbines. But advantage is that maintenance is low, and at the same time, any direction of the wind it can be rotated. Another important design, if you see it, it has can say a mixed mode. Savonius is at the center, and Darenius is at the side post. It is there. This mixed type of design, a hybrid design, is also followed. In that case, the drawbacks of the two designs are nullified, minimized, and advantage is maximized. So various types, but still almost can say at a developing stage it is going on. But nowadays, almost can say for the last decade, there is a renewable interest in the case of renewable energy. These are some of the diagrams across the world people are utilizing. Across the roof they are using, top roof they are mounted, and this vertical axis also it is mounted. And sometimes what happens between the two buildings, the venturi effect is there. So due to venturi effect, what happens? The wind velocity increases. So one can install the wind turbine to take the advantage of high velocity of the wind. So almost can say we have discussed about horizontal axis wind turbines and vertical axis wind turbines. So if you summarize what is going on, in that case you will see that vertical axis wind turbines are less efficient than horizontal axis turbines. That is a drawback as compared to horizontal, and that as compared to vertical. Horizontal axis wind turbine is better for large size applications in terms of megawatts, whereas vertical axis is suitable for the case of small scale, means in terms of kilowatts they are suitable. Major problems may arise in vertical axis wind turbines to handle the static and dynamic loads for large size applications. So large size applications are still at a developing stage for vertical axis wind turbines. But still there are advantages for the case of vertical axis wind turbines. They are attractive for smaller size applications, rooftop or for building integrated solutions, do not require any yaw mechanism, means you don't have to control, they are independent of the direction of the wind itself. Pitch regulations or gearbox is not required. They have few movable parts, that is from maintenance point of view this aspect is important, and therefore obviously maintenance cost is low. Now if you utilize a small capacity wind turbine, in that case for small size turbines the environmental impact is low, because you see whenever you install a big size turbine, then the point is that transportation is there. If suppose in the jungle, if wind velocity is good, then we have to cut the trees, we have to construct the roads and other aspects are there. Ultimately, even in wind energy also, some environmental impacts are there. But if it is a small size turbines, the environmental impact is low. They do not cause instabilities in the power network systems, and they do not need large power storage capabilities. The small scale distributed generation energy systems also they are suitable. So each system has its own advantage as well as disadvantage. But the point is that for a small scale purpose, this vertical axis can play a very vital role. Now, there are certain issues and challenges are there in the wind energy. First, I will discuss about the operating parameters, coefficient of performance. Normally, ideally, as per the Benz law, Benz frequency, 59.3% is the maximum power output you can take from the available wind energy. This is theoretical. Modern wind turbines, almost well-designed turbines, they can abstract up to 40 to 45%. So therefore, their coefficient of performance is 0.45. Besides this one, the blade angle is kept in such a way that is known as the pitch. That at what angle because the angle is provided on the blades, so that angle is quite flexible, and based upon that one, based upon the wind velocity, this angle can be changed, and that is known as the pitch itself. The tip speed ratio also play important. Tip speed means the radial velocity of the wing divided by the velocity of air itself. This direction, this is important because the point is that if this velocity ratio is high, in that case, it is not preferred. The reason is that in that case, the wing will not get fresh air. If this is very slow, in that case, the air will pass through between the two wings. Therefore, this tip ratio should be optimized in a very proper way. Because this is a this is optimization parameter. Based upon that one, the wind turbines are designed. Solidity is the portion along which, because how much portion the material existing in a wind turbine. So higher is the material, in that case, the speed will become slow. Less is the material, the speed has to be fast. In between these two conditions, one have to optimize the wind turbines. The number of blades versus TSR is a very important parameter. And earlier, you see, in the case of small size wind turbines, number of blades was quite high. But later on, it was recognized that not more than 3 blades are required. So most of the wind turbines, in terms of megawatt capacities, the optimum value of wings are 3. Torque play an important role, because the point is that I can say the minimum velocity to create a torque is, it should be, if the velocity is more than 2.5, then the wind velocity will be there and the rotation will take place. So sometimes the turbines which require higher torque, in that case, some battery system, using the battery system, you have to give the initial torque, power input to the turbine to start the turbine. Once it is started, then the supply is stopped and then it will start generating the power. These are the important parameters which are important when we analyze a particular wind energy source, wind energy turbine. Even wind energy, when we say that renewable energy, it is there, but the point is that this is a diagram which indicates, of course, next 40 to 60 years, by application of wind energy on the land, the temperature may rise from 0 to 1 degree. 1 or 2 degrees may be there. So, but this is almost, can say, a lot of controversies are there. Some people say that temperature will rise, some people say that it will not rise. But can say this is the prediction based upon those scientists who have done the analysis, and they say that due to wind energy also, the temperature of can say temperature changes due to the deployment of large scale wind turbines, and the red color means rise in temperature, it is there. And this is on the scale of 40 to 60 years meantime. Now, I would like to inform you that DST has recently ask the proposals for small scale wind turbines. Even if you go to the website of DST, then the last date is 14th of April, where the DST also told the institutions and industry to give proposals for the case of small scale wind turbines also. So anybody who is interested to start their research in this area, they can apply in the DST. One of the important component, wind turbine, why it is costly? Because the point is that tower is required. And if you construct the tower by steel, the price will high. So here recently, this Canada and Nepal, they have collaboratively done some research studies in which they have determined that they have used the material bamboo, and up to bamboo they can construct a triangular type of low cost triangular lattice towers, and the life will be 5 to 7 years, and after that you have to replace that one. So this is the low cost type of lattice towers. One can use it, and in that case the total cost can be drastically reduced. But in that case again, all your mechanics, static mechanics and statics and dynamics you have to apply as far as the strength is concerned. So material properties and structural analysis is part of that one, and for this particular tower is suitable for 500 watt wind turbines at localized zone where the grid is not available or remote areas are there. This kind of systems are quite suitable. So that's why tower cost one have to think, and this can reduce. This has a potential to reduce for cost in the case of small wind turbine for developing countries. This is the recent studies done by in collaboration of Nepal with respect to with Canada. Normally, in the development of wind energy, from administrator point of view, they ask that how much employment is generated. This is a well-known fact that wind energy generates maximum employment as compared to other renewable energy sources. This is the total estimation, and the bar represents the summation of offshore and onshore wind energy. Initially, it was only onshore, and I also discussed only onshore. Offshore wind energy also play an important role. So these two components, light blue is for the case of offshore wind energy, and dark blue is for the case of onshore wind energy. So up to 2008, the contribution of offshore wind energy was minimal, but as the time passes, 2010, 2015, the combination is that onshore wind energy has also included the employment, as well as the offshore wind energy also included. Even in 2020, you will see that continuously, if you see that in the future, the prediction for this employment generation is increasing. And of course, in 2020 and 2025, the offshore wind energy will play a very important role as far as the employment is concerned. That's very important. Why this data is important? Because ultimately, you can say from administrator point of view or planner's point of view, this is a very important data and encouraging data to expand the wind energy, which generates the employment. Now, if you look at the research area, almost wind energy is an interdisciplinary, interdisciplinary type of research. Location we can find out from GS already, because we have indigenously a satellite has been sent into the sky in the space where for different locations GIS information will be very, very accurate to find out the location, and GIS based calculations are now becoming an integral part as far as the wind energy resource assessment is concerned. Material science again play a very important role for blade composites for the blades and alloys. Computer science, overall control, design, analysis and monitoring point of view. Then aerodynamics play a role in the case of blade and rotor design, because stability and reliability is an important aspect. Analytical design and analysis methods are also required. Testing and monitoring the laboratories. And besides this one, power electronics, that is which takes into account the various factors, variable speeds, generators, electric network, all these things are there. So basically, if we want to start the research in wind energy, this includes structure point of view, civil engineering is required. Then mechanical engineering is required for wings and other part, mechanical, this gearbox and other things. And besides this one, the electrical engineering is required. So minimum almost combination of electrical engineering, mechanical engineering and civil engineering. A combined research in these areas can give a breakthrough, and they can, in a real interest, they can find out an optimum solutions as far as the wind energy is concerned. Now, this total discussion was onshore wind energy. Recently, a lot of thrust has been given in the case of offshore wind energy, and this will play a very, very important role in the next decade. Almost all the big countries, including Asian countries, they are investing heavily in the case of offshore wind energy, means it is inside the sea itself. You'll see that here a installation of wind turbine is there in the offshore inside the sea. The reason why everybody is going to inside the sea is that almost in the particularly Europe and other countries, the land availability is a big issue. Even in our country, land acquisition is a big issue. The point is that, and further another important reason is that the same source, whenever the wind flows over the sea also flows. So due to that reason, what happens? The velocity which you are getting on the sea is much, much higher as compared to on the land, because on the land is stationary, and due to that force, the wind velocity reduces. So due to that reason, a wind turbine which gives 2 megawatt on land, the same wind turbine can give around, say, 3 to 4 megawatt in the case of sea itself. Just almost can say 50 to 100% higher in the case of power output, because in that case the wind velocity is high due to less drag. So almost you can say offshore wind energy, because a lot of work is going on, and if you just look at the data, up to if you just look at the data of can say China, almost up to 2012, 1 gigawatt already they have installed, and 2015 the total capacity will be 5 gigawatt. 1 gigawatt is equal to 1000 megawatt, because such a unit, because almost you cannot install one power plant inside the sea. You have to install 100 by 100 or 1000 by 1000, because then only the economically viability will be there. So in this particular list, UK is the highest in the European countries, because UK don't have a land. So almost UK has entered into the sea, and they have installed the offshore wind powers. Then the third number is the Germany and USA, they are coming. And in this particular list, India's contribution is unfortunately negligible. Recently, they have installed around, say, 1 gigawatt, they have planned for 1 gigawatt power plant near Rameswaram, and one demonstrative plant, pilot project in Gujarat, 100 megawatt, they want to install that one. So activities has been installed, government has initiated the policy of offshore wind energy, but we are lagging as compared to the China. So China in a big way coming to the offshore wind energy. If you just look at this diagram, you will see that in 2010, this is the bright spots are the load centers, and expected load centers in 2035 is the almost the bright intensity of the spots are increased. Means in terms of power, if you just look at, then the point is that this you can say across the world, almost you can say a very high capacity terawatt, almost can say the requirement energy demand in 2035 34 in 2035 34,900 terawatt hours. It is a very huge quantity is there. So due to that reason, what happens? But see that these power centers are near the sea, and why this power centers are near the sea? The reason is that most of the power will be supplied through offshore wind energy. So therefore, a huge amount of, almost you can say that in our country, from Gujarat, Maharashtra, and Karnataka, the western coast is considered to be the economic center of our country. Whole economy is governed by from that particular portion. So in that case, how for next generation, what is the source of power? It is the offshore wind energy will play a very important role to supply the power to the industry, and then only the economic development will take place. Across the world, you can see almost you can say this is USA also, and the east coast, west coast, then Africa and China, this west coast is there. Almost as a huge amount of electricity will be required. But the main thing is that in that case, certain challenges are also there, where the challenge is that project cost is quite high. Almost 33% is the installation cost. Means the point is that wind energy turbine design is already available, but the foundation cost and the pillar cost is the biggest one, because the 80-meter height from sea level, it has to rise, and at the same time inside the sea depth is also there. So when the sea depth is low, price will be less, but when the sea depth is high, in that case the foundation cost will certainly increase. So it is there, higher installation cost means 33% of project cost it is there due to sea operations, difficulties during the construction and preparation phases, and overall cost is quite high. But if you think in terms of gigawatts, means minimum 1000 megawatt in the order of that magnitude, in that case the price can be reduced. So, in our country, most of the cases, what happens, till now we don't have all these type of vessels, and due to that reason, what happens, we have to import it, and per day the charges are quite high. Due to that reason, the cost is around 10 to 20% higher as compared to other sources. But certainly, if you go in a big way, if you plan in a certain way, in that case, the price will be reduced. Just like solar, initially the price was 15 rupees per unit. Later on, as the mass scale production has taken place, the price is reduced less than 5 rupees per unit. The same way in offshore energy, one can think about the same trend. These are the important vessels, almost can say Koreans, they are manufacturing those vessels, and these vessels are necessary for installation of wind power. And since they have to work in the wind velocity of say 5 meter to 10 meter per second inside the sea itself. Offshore energy, the role of oil and natural gas industry can play a very important role, and since they have already an experience of foundation and installation work, so their experience can be utilized for installation of wind energy, so wind energy towers. Certain case studies also we have done in the case of this offshore wind power, where almost we can say we have bathymetry data, foundation technology, and competing uses. Out of that one, what happens, the 60% of that area is not utilized, because others 40% we have to subtract. The reason is that those 40%, due to some can say shipping areas, some environmental point of view, one have to acquire, and you cannot can say acquire those areas because due to certain reasons. So one is the left hand side aspects, it is important. Another is the wind data source through satellite or through various other sources we can collect the data, and then using those data we can convert the wind speeds at a particular hub height where we install the power plant, and then we can convert them into power density and power output per turbine. Say for example 3.6 megawatt curve you can use, you can install a 5 megawatt depending upon the capacity of the power. So almost one small case study we have done for the case of Gujarat coastal areas, and in that case a different almost can say western coast includes the total can say this includes the almost can say Gujarat around 1,608 kilometers. This coastal length is there. Besides this one, Maharashtra zone also we have selected. Now this is the coastal where total coastal length of Gujarat is 1,608 kilometers and Maharashtra 800 kilometers. So it will be around 2,400 kilometers. It is there. Besides this one, nowadays almost international level an agreement is there. That particular zone, green zone, decided is this is EEZ, exclusive economic zone. Now this is almost up to a coastal area, nautical miles up to 200 nautical miles. This is almost as a central government of that particular country can utilize it for resources purpose. Each country almost you can say up to 200 nautical miles can enter into the sea, and they can utilize it for any other resource extraction purposes. So this is the almost as a recent development. A couple of years back the agreement was there, and based upon that agreement our EEZ zone is fixed. This EEZ zone, that is exclusive economic zone, will play a very important role in the next decade, because most of the resources will be from marine biofuel can also be produced, then wave energy is also there, then your tidal energies are also there, this offshore energy is there. So through the sea, the next decade will belong to this particular zone. Now based upon this one, the point is that there are foundation technology. You will see that where the sea depth is less, you can use a monopile, and when sea depth is higher, you can use a tripod. Then you can use a jacket type for that particular purpose. If sea depth is between 50 to 200 meters, in that case floating type of wind turbines are used, and floating type still at a developing stage, they are quite expensive. But monopile technology, when the depth is less than 50 meters, this technology is well established and one can easily use it for installation of wind towers inside the sea itself. These are the different can say literature it is available for different height, different can say gravity based structures, monopiles, tripiles, they are available, and these are the diagrams of the wind powers, GBS systems, monopile systems. Monopiles is a well established technology, particularly you can say oil offshore they are using, and easily one can install, and the same technology can be utilized for the case of wind towers. When the depth is high, one can use jacket frames, tripile, tripod, it is used, and if it is more depth is there, then floating type TLP, SSP designs, spur floaters. So across the developed world, they have started doing research in that area because they know that after 10 years, this source will play a very important role. So research has already started. In our country, a thrust in the offshore energy is still lacking, and academic institutions can play an important role in the case of offshore wind energy. Again, a vertical axis turbine, almost can say very few, but in Sweden, almost October 6, 2015, they have installed, and company name is Ropatech Turbine Offshore. They have installed this vertical power plant. So our study says that we have find out in the Gujarat region what is the depth available for 0 to 10 meters, 0 to 20 meters, 20 to 35 meters, and based upon that depth, we have counted that how many GE turbines of 3.6 megawatt can be utilized for that particular purpose and how much power output they will give. Out of that total area, that blue color area is there, out of that particular red, light yellowish, and this maroon color, out of that 40% area we have to subtract, and after subtracting that area, we have calculated that total annual power generation is around, say, can say it is total power generation by the western coast, it can give 0.7 into 10 power 6 gigawatt hours. As I have told you, the total requirement, estimated requirement in 2021 is 1.9 into 10 power 6 gigawatt hours. So almost a Gujarat coastal area, Gujarat and Maharashtra coastal area can give less than 50% of the total requirement of the country itself. So that's why this offshore wind energy is considered to be a huge quantity. But the point is that investment must be done in a judicious way. A lot of planning is required in that case. But as far as the resource is concerned, this is considered to be a very huge source among all the renewable energy sources. And even a single turbine, almost in Scotland, they have designed up to a single turbine of 7 to 10 megawatt. A single turbine can generate up to 10 megawatt. This is a huge quantity. So that's why my objective was to tell you that this is the development going on in the next 10 years, where wind energy, by means of offshore wind energy, it will play a very important role. So this is almost, you can say, we have EEZ, we have classified, and based upon that one, we have also done the study for the case of total EEZ, exclusive economic zone also, and we have identified the areas where we can install the power plants and wind power plants, and based upon that one, we have done a calculation where how much area up to the depth 30 meter less than it is available, less than 50 meter how much depth is available, and around 50 to 120 how much area it is required. So based upon that one, a planner can take a decision, or an investor or a developer can take a decision whether based upon how much cost it will be required, because these are the initial data. Based upon that one, the decision making is taking place. Out of that one, we will see that area, can say, environmental point of view, which area we have to subtract, which are the most can say busiest area, we cannot use it. So high impact area we have to exclude due to shipping lanes, fishery rights, other things, and low area due to environment also we have to reduce. So only the medium scale human impact areas are there. Those areas we can select it for the case of offshore wind energy. So this analysis also at par with the developed world people are doing. So we have done these studies to find out that which is the place suitable for offshore wind energy. So these are based upon the classification of wind power classes. We have classified the areas, and class 1, class 2 and class 3, a huge amount of area is developed, and in a planned way if you go, in that case next 1 decade almost we can fulfill the requirement of the country's demand as far as the electricity is concerned, and offshore wind energy is sufficient to fulfill that one, besides onshore wind energy. So these are the contours for the case of annual wind speed at 80 meter height and annual mean speed at 80 meter height, wind power density. So because all calculations are required, based upon those calculations one can take a decision, right? And these are the monsoon season. You will see that highest monsoon season, what happens, almost you can say here the huge quantity of wind power is available, where the northern India the scarcity is there. So this particular offshore wind energy can fulfill the demand at a peak load also, and during the peak load the electricity requirement, if any source which fulfills the peak load demand, is considered to be a very valuable source. Now normally you can say heavy investment is required. So due to that reason, one have to see that how many cyclones are there in the case of this Arabian Sea as compared to the Bay of Bengal. So you will see that in the case of Gujarat, the less cyclones are there as compared to other parts of the country. From that point of view also it is good. If you just look at the cumulative part, almost you can say huge number of activities, almost 2012 onwards, the total wind power, cumulative power is continuously rising, exponentially rises there. So trend is towards the wind energy because it has a less impact on the environmental point of view. A very important graph, you'll see that already when we have this particular left hand side graph represents the distance to shore, that is in terms of kilometers, and right hand side is the water depth. So wherever the depth is less than 50 meters and the distance from the shore is less than 100 meters, most of the places people have already planned. In the case of European countries, the projects are going on and they have already made the planning in such a way that they will install the offshore wind energy in that case. Again, another diagram, water depth less than 100 meters and distance to shore is around say 200 kilometers. Almost most of the projects are at the planning stage, they have started. A lot of skill development opportunities are there in offshore wind energy. Interdisciplinary areas are there, they have to be involved, and this is a must. Therefore, even the courses can be started in the case of offshore wind energy. And economic analysis also we have done. And economic analysis, what happens? It varies from, say, for example, if the investment is high, so due to that reason, the initial price may be around, say, 10 to 11 rupees per unit. But slowly and slowly, if a judicious way, if indigenously some manufacturing takes place, in that case, price can be reduced up to 5 to 6 rupees per unit also. I will not discuss about this this economic analysis. You can get in the literature the figure of 11 rupees per kilowatt hour. In the beginning, it will be there. Later on, it will be reduced. So this almost sensitive analysis we have done it with a capacity factor of 40% capacity factor, which is quite high in the case of offshore wind energy as compared to the onshore wind energy. So based upon this analysis, we have done these studies. And lastly, let me finish this particular talk. The Reliance, the man from Reliance, Dhirubhai Ambani, a well-known name, and he has given that. As far as the industry is concerned, we have to think big, think fast, think ahead. Ideas are no one's monopoly, and particularly in wind energy, this fantasy is quite valuable. The reason is that whether it is a small scale or big scale, you have to think in an innovative way. The things, most of the books, what happens, the information available is old information. They say that economic is not viable. They are 20 years old information. In the modern context, the point is that one have to again analyze the problems because generator design has changed, wind turbine design has changed, tower design has changed, and your data collection information has been changed. So within this modern context, one have to think in a proper way, and again we have to revise the designs and let us see that how we can achieve in the case of wind energy. Thank you very much.